Ami, אנחנו מוכנים. Okay, so I wrote here on this board the steps in showing that the integral from 1 to infinity of sine x over x in absolute value diverges. Now I'm not going to go over them. You can try them on your own, and if you're looking on the video, you can press pause and copy all the steps, because I'm really not gonna waste time on this. It's an exercise. It's very similar to the stuff we did last time, and the conclusion is number 4, that this diverges, and therefore the integral from 1 to infinity of sine x over x converges what's called conditionally, which is the opposite of converging absolutely. In other words, it converges, but in absolute value, it does not. Okay. One last thing that I want to do to wrap up this topic of improper integrals before we move on to our next topic is the following. So, question. Assume that f is non-negative, so it's greater than or equal to 0 for every x, continuous, and the integral, let's say from 0 to infinity, of f of x dx converges. So these are the assumptions. We have a continuous non-negative function whose integral from 0 to infinity converges. Is it true that the limit of f of x as x goes to infinity equals 0? When I say is it true, I mean, is it necessarily true? Does this have to hold? In all the examples that we saw, it did hold. We saw e to the minus x, we saw 1 over x squared, remember those? In all of them, making the integral converge when you go to infinity, 0 is not essential here. Put any a. It's a bounded function. That's the issue is not unboundedness. The issue is at infinity. So in order to make the integral converge, in order to accumulate the area at a rate that allows the total area to be bounded, we kind of had to have the function approach the x-axis, go to 0 as x goes to infinity. Does that have to happen? So if you're going to say it does, you have to kind of give a line of argument. Okay? And if you're going to say it doesn't, well, the best way to say it doesn't is to give a counter example. Okay, yes?
1 over x squared plus 1?
1 over x squared plus 1, so if you take 1 over x squared and you add 1, this is no longer going to be true. It's not going to converge, because there's going to be a rectangle of height 1 sitting underneath there, an infinite rectangle of height 1, and it's no longer going to converge. Yes?
Sine of 1 over x?
Sine of 1 over x. Ooh. Sine of 1 over x. It's not non-negative. Okay? Non-negative. So you can't have cancellations of area. We know that when we do cancellations of area, weird things can happen. But non-negative. No cancellations of area. Yes?
I don't know an exact formula, but some function that approaches infinity at infinity and goes to 0 when it approaches 0. Like some kind of e to the minus...
But if it approaches infinity when you go to infinity, there's no way this integral is going to converge. If it goes to infinity, the area there, intuitively, I'm arguing intuitively.
1 over x is also going to infinity. So,
No, 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 no. That we said choosing 0 here is just, you can choose 1 or 2 or 5 or whatever. It's not the issue of an unbounded function. Okay, the issue is that we have infinity here. It's an infinite interval. If it goes to infinity at infinity, that's, I mean, the worst case scenario. Okay, so do you agree that intuitively we really want to say that this is true? Right? Naive intuition says, hey, I want to accumulate less and less area. It better go to 0. Do you agree? And if you look at those pages with the functions and graphs that you have, the example that I'm going to draw now should be on there. It's the counter example. This is false. Okay? And it's not easy to come up with on your own. It's rather tricky. And the idea is that you do want to accumulate less and less area, but you can do it differently than just descending to the x-axis. And here's the counter example. So the answer is no. And here's the counter example. I'm not going to give you a precise formula for the counter example. I'm going to draw it. You can come up with the formula if you really insist on it, but it's not, it doesn't make things clearer or anything. And the counter example is the following. I'll draw it in blue. So here are the integers. Here's 1, here's 2, here's 3, etc. These are the integers. And here's 1 on the y-axis. And the function is going to have the value 1 at every integer. It's going to be 1 here, and 1 here, and 1 here, and so on. On every integer, it's going to have a value of 1. And it's going to be, I'm going to call it a tent function, because it's going to look like a bunch of tents. And what it is basically, so around, centered symmetrically around each integer, there's going to be a tent like this. In blue is the actual graph of the function. And the difference between the tents centered at each integer is that they're going to get narrower in width. Their base is going to become smaller. So here the tent is going to have, and it's going to be 0 between the tents. So it's 0 here and 0 here. And here the base of the tent is going to be of size 1, from 1/2 to 1.5. Okay? And then here the base of the tent is already going to be of size 1/2, from 1 3/4 to 2 1/4. And then here the base of the tent is going to be 1/8, like this. And in between the tents is going to be 0. And so on. And I claim that this is a counterexample to the so if you go all the way out and suppose you're here at some integer n, here's n, so there's a dot here, and at n you're going to again have this tent. It's going to look very skinny, and dot. So is it clear even without prescribing the actual formula? I mean, you can give a case formula. These are all linear, and you can calculate them and give the actual formula, but it doesn't help in understanding this. Do you understand what I drew here? Is it clear what's drawn here? Now let's see that it has to satisfy 4 things. So first of all, is it true that it's a non-negative function? Obviously, it's clearly drawn above the axis. Does everybody agree? Okay. Is it true that it's continuous? Answer, yes. It's just gluing together linear functions, and I can draw it without lifting the pen off the board, except for at the dot, dot, dots where I have to. Clear? So it's continuous. Let's discuss this in a second. Is it true that its limit, as x goes to infinity, is not 0? In fact, it doesn't have a limit. I mean, this is like, you know, the monitor of the heartbeats of a patient. This is a patient that just is not willing to die, right? Well, they get smaller, but, you know, you can go way out there, and then once you hit an integer, bloop, and an integer, bloop, right? So do you agree that this thing has no limit? Do you agree? It's always going to have ones and zeros and everything in between, no matter how far out you go. Yep. So this does not hold. So in order for this to be a counterexample, the only thing remaining to show is that the integral from 0 to infinity converges. Do you agree? Wait 1 second. Why does the integral converge? Well, so let's call this function, ready? I'm going to call it f. Ha. Okay, now you can call it the tent function or the triangles function or the heartbeat function or whatever. So what's the integral? The only thing we really have to calculate something is to calculate this integral. So the integral from 0 to infinity of f, where f is this function, is what? It's wherever it's 0, the integral, there's no contribution to the integral. We just have to calculate the sum of the areas of these tents. Do you agree? So it's the sum. It's an infinite sum, which is a promo for our next topic, which is infinite sums, namely series. So here's our first series. So it's an infinite sum of triangles. So how do you calculate a triangle? You need its height. So what's the height of a triangle centered at the integer n? 1. It's always 1. Times the base. So what's the base? It was 1 here, 1/2 here, 1/4 here, or what? 1 over...
Can you say 1 over n?
1 over 2 to the n minus 1, right? Because at 3 we want 1/4. So it's going to be 1 over 2 to the power 3 minus 1. So this is the base, 1 over 2 to the n minus 1. Do you agree? Yep. And then you have to multiply by 1/2, because the area of a triangle is 1/2 base times height. Right? So all in all, we get this sum, n equals 1 to infinity, of 1 over 2 to the n. Do you agree?
Can you say that again?
N minus 1.
This?
The 2n minus 1?
Why is it 2n minus 1 and just not?
Because at 1, you want to have base of 1. So it's 1 over 2 to the power 1 minus 1. Gives you 1. At 2, you have a base of 1/2. 1 over 2 to the power 2 minus 1 gives you 1 over 2. And so on. Good?
Why
Okay.
don't you put n there though instead?
Because then it's not what I drew. If I put n, then at 2, I would have 1 over 4 here. And it's not 1 over 4. I said it's 1 over 2.
Okay.
So if I want to represent this, I need this. So what is this sum? Okay, so there are various ways to calculate it. In fact, we already did. This is precisely 1, what is it? N starts from 1. So it's 1/2 plus 1/4 plus 1/8 plus 1. Remember that? This is precisely this thing. 1/2 plus 1/4 plus 1/8 plus 1 over 16. Remember this? So I'm not going to continue. I did it longer last time to brag that I know powers of 2. So what is this equal? 1. And we'll see later today other ways of calculating this. This is just a geometric series. Okay, it's easy to calculate. There's a formula for it. But there you have it. The integral of this function is 1. It converges. The total area is 1. And the way to accumulate less and less area is not by descending down to the x-axis, but rather by throwing in smaller and smaller chunks of areas as you go further out towards infinity. Okay? Question, yes.
Could we have used the example sine of 1 over x plus 1?
Sine of 1 over x
No,
is
sine
not...
of x over x plus 1.
Sine of...
X over x plus 1.
Yeah.
Always positive.
Look, if you take a function... okay, we can discuss every example in particular, but if you take a function that you know that the integral converges, and then you do a plus 1 to it, it's no longer going to converge.
No,
But it gets
Okay, wait. It's hard to concentrate. You're saying, I'm not even sure that both of you are saying the same example. Let's discuss it over the break, okay? But my guess is no, okay? The way to do it without cancellation of areas is going to be via something like this, okay? Yes?
For this example, it's possible to create a rate of how it's going to be less the base, such that it's not going to converge. Like if the rate of the base is going to be smaller each time, but it's going to be...
Well, you're saying, what if I don't make the bases half of the previous one each time, but 1/3, or... So all these questions of this form, are really related to series. When is the series going to converge?
Right.
And the answer is, tune in next time. Next time is in 2 minutes for our discussion of series. Okay? So let's just do it. So is this clear? Okay? So I want you to remember this. Well, first of all, it's a promo for series. That's a good reason to end our discussion of integrals with this. But also remember this example. It's going to be a counterexample for some other things if we have time for them. And I'm going to challenge you and ask you, and I'm going to leave these as homework problems. So what if I rephrase this question and require exactly the same thing, but removing this greater than or equal to 0? What if I require that the function is strictly positive? Same question. This is no longer a counterexample. Do you agree? This counterexample relies heavily on the fact that this function is most of the time 0, right? Is it true now?
Yes.
It's a homework problem. Do you live here? Is this your home? It's not. So don't answer now. Okay. You do? No. Okay. So that's question number 1. What if I remove this assumption? Okay. So that's homework 1. Is it still true? Okay. I'm not saying the answers. I'm leaving it. No, I'm not going to tell you the answers. I want you to think about it. Struggle. Come and ask. But first think about it. If it were that trivial, I wouldn't waste time on it. It requires thinking. You already saw that there's non-trivial stuff going on here, right? Try to think about it. It's a challenge. So that's homework number 1. This instead of the less than or equal. Okay? Homework number 2. Suppose I add a requirement. So let's write homework number 2 in blue. Homework 2, same question, but adding a requirement that the function is also monotone. Monotone. That also makes this counterexample completely irrelevant. This is not monotone. This is up, down, right? So what if I require that it's monotone?
Strictly greater than 0 or just
Here?
greater or equal than 0?
Oh,
When you add that, you can go back to greater than or equal. Okay, if you can do each one by varying just one thing of the original. And yeah, okay, there's a homework 3, but it involves something we never discussed. So I'll just leave it at this.
Ask the homework for those who want to do it.
Hmm?
Would you just like write down the homework for those who want to do it?
Yeah.
No, number 3.
No, it requires defining something that we never defined. And if you want to, come up to me later and I'll tell you. Okay. Okay, so this wraps up our discussion of improper integrals. And what I want to start now is the topic of series. Okay, so this takes us back to something we discussed at some length a while ago, which is sequences. Okay, remember sequences? Those ANs? Okay, so there's going to be something that, a major change here. Our sequences are no longer going to be ANs. Ready? They're going to be AKs. Because N I'm going to need for something else. So AK, let AK be a sequence. Sequence. And the sum k equals 1 to infinity of AK, and this is just shorthand notation for A1 plus A2 plus A3 plus dot 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 dot. It's not a finite sum, it's an infinite sum. So this thing is called a series. I find it very confusing, the fact that one of them is called a series. That sounds really plural to me, but turns out to be just one. Okay? So this is called a series. And if we stop not at infinity, which means don't stop, dot, 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 if instead we go only up to n, so what's this? This is a finite sum, right, of just the first n terms of the sequence. So this we're going to denote by Sn, and that's where I want to use the n's. And this is called a partial sum of the series. Okay? So there are many partial sums. This is the nth partial sum. Okay? So yeah, definition. We say that the series sigma k equals 1 to infinity of AK converges if the sequence Sn converges. If there exists a limit to the sequence of partial sums. Okay? So if you think of it for a second, it makes sense. So these partial sums, when n goes to infinity, you're summing more and more terms. And when n goes to infinity, you're getting the infinite sum, which is the series. So if this thing has a limit, we say this is the limit. And we say that it converges. Okay? So if there exists a limit, and again, when I say exists, I mean finite. Finite. Limit to the Sns. And we declare that to be the sum of the series, or just the series. Okay? Is this clear? Okay, and otherwise we say that the series diverges. Let's do an example example 1. So let's look at sum 1 over 3 to the power k. So what is this thing? When k equals 1, I get 1/3. When k equals 2, I get 1 over 9. When k equals 3, I get 1 over 27. K equals 4, I get 1 over 81, and so on. Right? So for example, this is A1. What's this thing? S3, exactly. It's the sum of the first 3 factors, right? Okay, and this thing, 1 over 3 to the k, this is a k. And then there's again a dot, 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 of course. Okay? So it's a sum of the elements of the sequence. Okay? What is Sn? So Sn is the sum of the first n elements. What kind of sequence is this? Geometric, right? Every term is some fixed quotient times, or some fixed ratio times the previous one. What's the ratio here? 1 over 3. Do you agree? So Sn is a geometric sequence. And do you know the formula for the sum of the first n elements of a geometric sequence? Something divided by q. Okay. So I'll remind you, it's A1, right? Times 1 minus q to the power n divided by 1 minus q. This is the standard formula. Okay, I hope you've seen it. Okay, I don't want to prove it now. You can fiddle around just a bit and actually prove it. I don't want to do it now. So what's q here? What's q here? So A1 is 1 over 3. 1 minus. Q is 1 over 3 as well. So q to the n is 1 over 3 to the n. Divided by 1 minus 1/3. Do you agree? In our case. Now what are we interested in? The limit as n goes to infinity of the sequence of partial sums, of this Sn. So what is the limit? As n goes to infinity, what does this go to? This goes to 0. Do you agree? So we get 1/3 divided by 2/3, which is 1/2. Okay? Hence, this series converges, and its limit, or its value, or what it is 1/2. So this is a way of writing the number 1/2 as an infinite sum. Clear? So that's example number 1. In general, so let's call it example 2. In general, if we take any geometric series, sigma k equals 1 to infinity, sum A1 times q to the power k minus 1. This is a general form of a geometric sequence, a geometric series. Then, what is the limit of the SNs? The SNs are going to be this thing, in general. And what's the limit? Depends on q. Okay, so if q is less than 1, then if q in absolute value is less than 1, then q to the n is going to go to what? 0, and therefore the sum, the infinite sum, the limit of the SNs is going to be what? A1 over 1 minus q. Then if q is less than 1, then the series equals A1 over 1 minus q. What if q is greater than or equal to 1 in absolute value? Then when you raise it to the power n, it goes to what? Infinity. And therefore, the series diverges. If,
What if A1 is 0?
if, 1 second, q is greater than or equal to 1, the series diverges. If A1 is 0, that's just saying that the series is the constant series 0, and it's a pretty boring situation. Maybe in the definition you should rule out A1 being 0. Okay? Clear? Everybody? Okay, let's do another example. So this was example 2. So our 10th function gave us a geometric series, if you remember, the geometric series 1 over sum of 1 over 2 to the k. And now you can calculate its sum using the formula we just derived and see that it gives you the same thing as what we got with a square in the kind of picture argument. So example number 3. Suppose we look at sum k equals 1 to infinity of negative 1 to the power k. Does it converge? And if so, what is the sum? So I'm getting different answers here. How do you determine? What do you have to do? What do you have to do? We're at the next question. Not does it or does it not. What do we have to do if we want to? We have to look at what is the sequence of partial sums and calculate its limit, right? What's the sequence of partial sums here? Sn.
1, negative 1.
So you start with the sequence you're summing is negative 1, 1, negative 1, 1, negative 1, 1. So what are the sums? Negative 1, then negative 1 plus 1, 0. Minus 1, 0. Minus 1, 0. So the sequence of partial sums is minus 1 or 0 depending on what? Depending on whether n is even or odd, right? So if n is odd, it's minus 1, and if n is even, it's just 0. Do you agree? These are the partial sums. Does this sequence have a limit as n goes to infinity?
No.
It doesn't. Therefore, this thing diverges. Clear? And it diverges in a different way than the geometric one where q is greater than 1. It's not that the sum you just add and add and add and go to infinity. It's that the sum you add, subtract, add, subtract, add, subtract, and just don't approach a limit. Clear? Everybody? Okay. And example 4 would be, for example, sum of k. K equals 1 to infinity. What about this one? Right, this diverges, and for what reason? Right, the limit of the partial sums is infinity. Right, you're adding bigger and bigger and bigger numbers. So both of these are called divergent, but in somehow a different sense. Clear? Everybody? Okay. Example 5. Let's do something a little more interesting. So the theory doesn't end with these examples. In fact, we're going to see just one or two more, and then we're going to make a kind of a tragic statement that usually we don't know how to calculate series. What is the plural? Just series, huh? You don't say serieses or seri or weird things, right? Okay, so example 5. So just like improper integrals, we're going to say that usually we don't know how to calculate the actual sum, but we do have various tests to determine if the series converges or not. Just like with improper integrals. And in fact, we're going to see that these things are actually related to improper integrals. You're going to see as we go along that there are some kind of points where they resemble each other, and then there's going to be a theorem that tells you how exactly they're related. So here's the next example. This is still one we can calculate. So k equals 1 to infinity, 1 over k times k plus 1. So I want to sum this, okay, and I'm going to make an observation here. After you know integrals, this observation is not going to shock you. Sometimes we teach series before we actually teach functions altogether, right after sequences, and then it's a bit more shocking. But the observation, so observation, I can rewrite 1 over k plus 1 as 1 over k minus 1 over k plus 1. Getting from here to here is just common denominator. Getting from here to here, you also know. This is what we call partial fractions, right? And using this observation, I can write what Sn is, and there's going to be a neat thing happening. So what's Sn? So I have to first write what A1 is. A1 is when k equals 1, but I'm not going to write this, I'm going to write this. When k equals 1, I get 1 minus 1 over 2. Do you agree? So 1 minus 1 half. This is A1 plus. What's A2? I have to plug in k equals 2. So it's 1 half minus 1 third. Right? What's A3? I have to plug in k equals 3. 1 third minus 1 fourth. Dot, dot, dot. And what's An? The last term in Sn. Well, it's 1 over n minus 1 over n plus 1. Good? And now, the neat thing that happens is what? Can you see it? Right, there are cancellations here. I have minus 1 half plus 1 half, gone. Minus 1 third plus 1 third, gone. Minus 1 fourth plus 1 fourth, gone. And I'm left with, at the end of the day, with 1, and the last thing, minus 1 over n plus 1. As n goes to infinity, the Sns go to 1, and hence this thing converges, and its sum is just 1. Yes? This is as formal as it gets. This is a finite sum. Okay, it's not an infinite sum. In infinite sums, you can't do things like this. We'll discuss it a bit later, but this is a finite sum. And okay, if you just you want to write it, you can do some form of induction, but that would really be, saying more than what's really needed. I think it's sufficient to just say this and it's obvious. Okay, So this thing has a name, this phenomenon, and it's called, do you know the name? Right. It's called a telescopic sum. And the reason is, if you think of a telescope, you know, the household telescope that people used to have, maybe some of you still do, not Hubble in outer space. It was kind of a thing like this that you open and close, right? That's kind of, you know what I'm talking about? Like a zoom of a very professional camera. Or think of pirates. So this is called so that's what's going on here, right? It's this, but then it's boils down to just this, and it's called a telescopic sum. So this is called telescopic. Okay, and when something like this happens, we can actually calculate. Okay. So let's start writing down theorems. Let's see what we can actually say that allows us to build up a theory without just calculating. I mean, if this was all there was to it, it would just be a discussion of calculating the limits of sequences, and that we already know how to do. So here's our first theorem. If a series converges, then the sequence that it's summing, not the partial sums, the sequence itself has to go to 0. This is in contrast to the last example of improper integrals that we saw, where we saw that you could have a converging integral without the function actually going to 0. In series, it can't happen. In series, if you have a converging series, the sequence has to go to 0. You have to be summing smaller and smaller and smaller terms, and that means it goes to 0. Okay? Let's prove this. This is like the shortest proof in this course, I think. Proof. So what is... Okay, so AK, I can write AK as SK. So the kth element I can write as the sum of the first k elements minus the sum of the first k minus 1 elements. Do you agree to this? Sum the first k, subtract the sum of the first k minus 1, you're left just with the last one. Does everybody see that? Now my assumption is that the series converges. What does that mean? That the partial sums have a limit. That this thing has a limit when k goes to infinity. Some limit, call it L. But if this goes to L as k goes to infinity, this goes to L as well. Do you agree? Because this is just a shift of the original sequence, doesn't change the limit. So this goes to, as k goes to infinity, L minus L, which equals 0.
Could you repeat just what L?
L is the limit of the sequence of partial sums, which exists because that's the definition of a series converging. Clear? Good? So that's the proof. And examples. So what example are we on? Example 6. So here's our first method. Well, this is not going to help us calculate, but this is going to help us determine when a series doesn't have any chance of converging. If the sequence doesn't go to 0, that's it. Too bad. Okay? So for example, if we look at the sum k equals 1 to infinity of 1 over the kth root of k. 1 over the kth root of k. There's a little k here. See it? So what is the limit of this sequence as k goes to infinity? 1. So ak equals 1 over kth root of k goes to 1 as k goes to infinity. And therefore it doesn't go to 0, because 1 is not the same as 0, unless you're doing integrals and ignoring the constant. And therefore this diverges. Clear? Good? Example 7. Suppose you have the sum k equals 1 to infinity of k divided by k plus 1, all of this to the power k. What's the question?
What is diverging there?
The series diverges because the sequence doesn't go to 0. If it were to converge by this theorem, the sequence has to go to 0. But it doesn't, so this diverges.
So there's some kind of e to something, right?
Good. So when you see something like this, a very good intuition is to say, hey, between all these k's, I can see an e. Okay? And it's going to somehow, we have to spell it out to see the actual e, but this smells like e. Sounds like e. Looks like e. Must be an e. Okay? So what's the limit of the ak's? So ak equals k over k plus 1, all of this to the power k. So let's write the reciprocal. So it's 1 over k plus 1 over k to the power k. And this we can now rewrite, oh boy, 1 over 1 plus 1 over k to the power k, right? And as k goes to infinity, this goes to 1 over e. I don't care what the actual value of the limit is. What I do care about is that it's not 0. And since it's not 0, the series diverges. Because if a series converges, the sequence it's summing has to go to 0. Clear? Everybody good? Okay. Of course, you can also say this about the geometric series when q is greater than 1. When q is greater than 1 in the geometric series, then the sequence itself goes to, well, doesn't go to 0. Right? You're multiplying by something that gets bigger and bigger. So it doesn't go to 0, and therefore it diverges. We already said it in a different reason, but okay. An important remark, you can write it here, is that the other direction to the previous theorem is false. And that's maybe the single biggest mistake in this course. So I'm going to I wasted the trick of emphasizing something with lots of colors last time. So I have to be even more, what am I going to do? The converse is false. Ha. False. Namely, what do I mean by the converse is false? You can have a sequence that goes to 0, but the series does not converge. Okay, so it is not true that AK goes to 0 as k goes to infinity, does not imply that the sum of AK converges. And a counterexample, we're going to see, we need a bit more tools to actually argue it, but we'll see it in a bit. So example, the sum of 1 over k. So this is a sequence that clearly goes to 0. 1 over k goes to 0, right? But the sum of 1 over k diverges. Okay? I didn't prove this yet, that this diverges, but we're going to do it.
This is about the rate that we were talking about the triangles before?
So yes, intuitively. This is intuition. Yeah. Don't try to put too much of your emphasis on intuition. You have to also relate to the formalism. But it is true that somehow this doesn't go to 0 fast enough. Okay? It goes to 0. You're adding smaller and smaller things, but somehow not smaller and smaller enough. Okay? But it's very, very tricky to put your finger or to develop intuition. I mean, I don't think I developed this intuition as of this moment, of being able to kind of recognize without running formal convergence tests and so on sequences that go to 0 and saying, whoop, this one converges, this one doesn't, this one converges, this one doesn't. So that it's a very, very delicate business. Our entire discussion of series is going to be on sequences that do go to 0. Because when they don't go to 0, that's the obvious case. It diverges. When they do go to 0, that's the interesting case. Does it diverge or not? Very tricky. Very delicate. Okay? Okay. So we'll see this fact a bit later. I want to write one more technical theorem and an example, and then we'll do the break. So here's another theorem. If some AK and some BK, and when I'm being sloppy, it's okay because it's kind of obvious that it's always a sum from 1 to infinity. So if both of these converge, then let's maybe write it as 2 parts. One, the sum of C times AK, where C is any constant, let's write this, equals C times the sum of AK, where C is any constant. And 2, the sum of AK plus BK. So if you sum the sequences first and then take the corresponding series, this converges and equals the sum of the 2 series. No plus C. Okay? And this is, it's crucial here that they both converge, otherwise it's false. Okay? And proving this is a straightforward argument. You don't have to do any epsilonautics. Straightforward argument of writing the corresponding limits of the sequences of partial sums. Okay, so it's really just standard limit arithmetics for sequences. Okay, you can try to prove this. So, example, huh?
And we can assume that the limits exist.
If it's an if theorem, if the limit exists, then these facts are true. if these are converging. Saying that they're converging is saying that the partial sums have limits. Okay, example what? What number are we on? 8. Example 8. So suppose we want to calculate, this is going to look scary at first, the sum k goes from 1 to infinity, negative 1 to the power k plus 2 plus 3 to the power k minus 1, all of this divided by 5 to the power k. Okay, and all of this thing lives inside the sigma. Okay, so what I'm going to do, well, looking at it, I want to, do you agree that it's a natural thing to do, to break it up into two series, right? And then they kind of look geometric-ish, right? So let's do that. So I'm going to write it as sum. So what do I have here? I want something to the k. So I'm going to write it as negative 1 to the power, what? I have a k minus 1 here. Okay, so so I'll do it like this. I'm going to write it negative 1 to the power 3 divided by 5 times minus 1/5 to the power k minus 1. There we go. I want to write it in as a geometric series. So here's the q to the k minus 1, and here's the a1. Do you agree that this first factor is precisely this? And the second one, no? Well, open this up. Think about it for a second. Is 1/5, wait, I forgot the sigma. Sum k equals 1 to infinity, 1/5, and then I have 3 over 5 to the power k minus 1. Think about this a second and tell me if you agree. Good? So here I have 3 to the k minus 1 over 5 to the k. I pulled the 5 out, that's this 1/5, and I have 3/5 to the k minus 1. Now it's geometric. a1 times q to the k minus 1. And likewise here, I took out a negative 1 to the power 3, so I'm left with negative 1 to the k minus 1. I took out a 5, that's this thing, and I'm left with negative 1 over 5 to the power k minus 1. Good? And this thing is justified, this move is justified by part 2 of the previous theorem, but this previous theorem is only justified if I know that both of these converge. Do both of these converge?
We don't know.
We do know. They're geometric. Do you see that they're geometric? They're a1 times q to the k minus 1 with q's which are less than 1 in absolute value. So they do converge. So this converges. Theorem part 2 tells us that their sum is this. Okay, and now it remains to calculate these, and that's just doing a1 over q minus 1. So let's write it where? Let's write it here. So what do I get? I get a1, which is negative 1 over 5, divided by 1 minus q, so 1 plus 1 over 5, plus a1 here is 1 over 5, divided by 1 minus 3 over 5. Right? That was the formula we derived for a geometric series just a couple examples ago. a1 over 1 minus q. Remember? When q is less than 1 in absolute value. And this is the hard part. I'm going to peek. What do we get? We get minus 1 over 6 plus 1/2, which equals 1/3. Good? Okay, so let's take a break now and continue in 10 minutes with more theorems of determining convergence of series. So 10 minutes. From here to here? No, you can do it.